Okay, welcome back to the Institute. A couple of students suggested that maybe I try out a sample magnetic force on a moving charge problem. So I have one here. It says a particle, either an electron or a proton, moves along a circle in a region of uniform magnetic field of magnitude 4.13 times 10 to the minus 3 Tesla, as shown in the figure. So you can see over here in this figure, it experiences a magnetic force with a magnitude of 3.2 times 10 to the negative 15 newtons. And then it gives charges and masses of electrons and protons. Now the first part that we're going to actually see here is the fact that our magnetic field is designated. Since they are actually represented with these little dots that are coming towards you, it means that it is coming out of the paper. Out of paper, or basically out of this surface. So even though I put an arrow on top of this, this is just to indicate that these are all the magnetic fields. So this is the magnetic field, but it's coming out of the paper. The particle is right here. It is this little, I'm going to make it green, this little green dot. And in this particular case, it is moving in this direction. So that would be the direction of its velocity. So using the right-hand rule, if we have it coming out of the paper, so in other words, if I put my index finger in this direction, so my index finger, this is going to be a picture of my index finger, is pointed that way, and I need my middle finger to be pointed straight up, or coming out of the paper, so I'm going to try to draw that. I can't really draw that. And then there's the rest of your fingers. Comes back into a thing, then your thumb would actually point in this direction. So this would be the direction of my thumb. So this is my middle finger. So this is my B. Yeah, let's change the color. So this is the direction of B, and this is the direction of V. And this is an absolutely horrible picture, but it actually shows that in order to go around in a circle, I know I need to have some kind of force that's toward the center of this circle. So my force should be in this direction, but since the thumb would actually point this way, it means that it's going the opposite direction of my right-hand rule. And if it's going the opposite direction of my right-hand rule, then it actually means that this particle is not positive, it must be negative. So this is a negative particle, which means that this is actually an electron. Now for solving for part B, that's actually not going to be a factor because the charge of an electron or a proton is exactly the same. But in terms of the right-hand rule, it tells us that it's moving the opposite direction. The second part that we're going to try to answer with this is, what is the particle's speed? So we're going to go ahead and use, for part B, the fact that our force is equal to the charge. Whoops, let's erase that for a second. It's going to equal my charge times V crossed with B. Now, in this particular case, my velocity is always going to be, it's going to be in the paper going around in a circle, and so its direction, the direction of the velocity, is in the paper, but the magnetic field is out of the paper, so they are perpendicular to each other. So when I solve for this force, I'm actually going to have the quantity of charge times my velocity, my speed, times the magnetic field. So it just equals that, because technically the sine, the next part, the sine of my angle, this would just be 90 degrees, so this whole thing would just equal 1, because the sine of 90 degrees is 1. I know the magnetic field strength is the 4.13 times 10 to the negative 3 Teslas. My speed is what I'm trying to find, so I'm just going to leave that as V, and my charge is going to be the charge of an electron, so that's my 1.6 times 10 to the negative 19. Apologize, I'm kind of getting this lumped together. And this should equal my force over here, which is going to be the 3.2 times 10 to the negative 15. So I could chunk all this out. Basically, to find my velocity or my speed, I'm going to end up multiplying the charge by the magnetic field and then dividing it over to the other side. So this should look like this. It should be my 3.2 times 10 to the negative 15 newtons. That's my force divided by the quantity of charge, 1.6 times 10 to the negative 19, multiplied by my 4.13 times 10 to the negative 3, which is my magnetic field. And when I calculate that out, I should get what my value for the velocity is. And when I get that on my calculator, it actually gives me a very big number. I'm going to change it to scientific notation, 4.84 times 10 to the 6 meters per second. Now I do have one more problem, this idea of the radius. However, I'm going to hold off on that. I'm going to come back to this sample problem a little bit later. I'll show you how to find that radius. It's going to be related to the mass of this object, but we're going to do that as a separate problem. Probably the hardest part about this is this right-hand rule. And if you remember, your index finger is always in the direction of your velocity. Your magnetic field is in the direction of your middle finger, and then your thumb points in the direction of the force. I'll see if I can also post a video where it shows that right-hand rule a little bit better, and maybe we can understand what's going on here. If you have any questions, just let me know, and I hope you enjoyed the Institute.